Yes, I wanted to wake everybody up before we got on the bus to go to the Hornet. So this is a work in progress, and it comes out of discussions between Greg Schmidt and I over the last year, thinking about, gosh, is there any interesting astrobiology that one can do on the moon? It's not immediately obvious where the prospects are, although it turns out that there are actually quite a number of people who have done some very preliminary poking around in this area. Now, the illustration that I've chosen by a good friend of mine is the ideal case where we have an astronaut on the moon, and he or she is looking at a big obvious thing that's sitting there, and it's quite different from the background. This is probably absolutely not what we're going to be able to see. So just a few words about the words that paleontologists use. A biocenosis is a whole bunch of creatures of some sort or another living together. If a big pile of stuff falls on them and they are trapped in that living association, then that's one type of deposit. Most fossil deposits are not of that sort. And so that's the other two words that we have here. Thanatocoenosis means a death assemblage. And this is typically a mixed situation where you have not only organisms living in a particular environment, but also things that are brought in. And you might consider that the moon is sort of the ultimate thanatocoenosis. So any material that has been lofted and eventually finds its way to the moon from giant impacts on Earth that carries astrobiological material, then is in this very different category of fossil representation. The issues with thanatocoenoses and an extension of those taphocenoses, which means really the taphonomic processing that happens to fossil materials, whether they be molecular or whole body fossils or whatnot, after they have died and come to the point of deposition, the moon could potentially be a very, very, very big thanatocoenosis. And the issues there, of course, that the time averaged assembly of these kinds of fossil deposits are very poor. Because you have a gamish of stuff all coming to one place, and then it's the paleontologist's job to sort those back out. And then, of course, for a transported assemblage, which we would have in the case of the moon receiving astrobiological materials, then we also have poor spatial fidelity as well. So we all know that dinosaurs really want to be immortalized. We're going to use dinosaurs as a proxy for paleontology, even though primarily we're certainly going to be looking for things that are far more nuanced and far smaller, undoubtedly. So the case study that really got me thinking about this actually comes out of some work that I found out about from David Kring. He and I were co-conveners on the third habitability, first billion years of habitability meeting last year that had to do with impacts. And impacts are certainly not my specialty, but I learned one heck of a lot. And so that sort of folded into my thinking. And David's colleagues and he have produced a paper very recently this year looking at potential Earth material perhaps being represented even in an Apollo sample that we already had. So that really intrigued me and got me thinking about this more, and chatting with Greg, we tried to figure out how we would actually approach this. So this is a first crack at this, and I think now that there's enough there to actually start putting these things together and synthesize some kind of comprehensive understanding of how one would go about trying to locate and identify astrobiological materials on the moon. So the easiest thing to do, of course, the most likely to be successful, is to have the lofting of material that's already preserved. It will already have experienced perhaps some diagenesis, some lithification, replacement on a mineral particle by mineral particle basis. And so it's already prepackaged, it's already rock in some sense. to be able to actually be lofted to the moon and find its way there. It's probably the only hope for body fossils of any sort. And alas, that probably is not going to be dinosaur bones, but microfossils do preserve very well in certain lithological circumstances, and so might actually be able to survive that process. The ejection of fresh biological material is very much more problematical. Is there any possibility for, let's see, is this my laser? Oh, that's a weird thing. Okay, I don't see it. All right, so something goes sploosh and puts a whole lot of biological material up, and some of it makes its way to the moon. Does that mean that dinosaurs are going to be raining out? Probably not. But there is the potential for some preservation, even of material that is not already lithified in some fashion or preserved in another way. So it's potentially true that fresh material could find its way to the moon and be mummified, essentially, because of the extreme desiccation, particularly if it were deposited in a place that was not subject to a lot of the deleterious circumstances that the lit surface of the moon experiences. All of this stuff is very hard to interpret, however, but this made me think about something that I have worked on for the last number of years that we have started calling geogenetic latency with respect to Earth. And this is how much biology can actually be stored in geology. And I don't mean fossil biology, I mean actual still viable microorganisms. This is a busy slide that I took out of another talk just to throw it in here to illustrate this. But the hypothesis is that some tiny fragment, some tiny fraction of the microorganisms in all earthly environments probably survive very rigorous diagenetic conditions and go on to remain viable until they're released again from subsequent geological processes like faulting or plate tectonics or impactors or something of that sort. And so we spent a lot of time thinking about who these organisms might be and how they would be preserved in a viable state. Now, from the point of view of finding them on the moon, we don't care if they're viable. These are going to be rock-eating organisms and chemolithotrophs and things that are not of human health significance. But the fact that they may be able to find their way to the moon and then be preserved subsequently is probably another potential pathway. So we know, certainly in the case of Mars, thinking even about the local panspermia issue, that there's significant potential for organisms to be packaged in rock materials that they are living in. And so this is why the great emphasis on organisms are actually part of the natural lithological biosystem in the crust of Earth, both on the land surfaces and in the ocean. So we have explored this whole idea of Mars and Earth and the swapping of genetic material, but it's also the important part for the moon is that these organisms are much more likely to be in their dormant and or resistant states as they are blasted out because of where impacts happen in rocky material. And so that is germane to the case of the moon. So where to look? Well, ideally, we want low-velocity impactors at high incident angles so that we get this low velocity and so that the emplacement is more gentle. There is significant work that's been done on this, of course, by Armstrong over a number of years trying to quantify this. And then other people have taken that idea and run with it and tried to do laboratory experiments doing simulated impacts. It's quite clear that permanently shadowed areas could minimize, of course, the damage that one would get from UV and solar particles, and that could act as collecting buckets. And this has been looked at by a couple of Russian scientists in a very obscure little thing that I just found the other day, where they look at this, the situation from the point of view of predicting where water ices can be, but they go through the exercise of figuring out what the deleterious effects would be in these permanently shadowed areas. of course, cave entrances. Those of you who know me know I love caves, and they're super cool. I point out that the first ever phase 3 NASA Innovative Advanced Concepts, 2 studies that have just been awarded in the last few months. One goes to Red Whitaker, actually looking at robotic access to lunar caves. And so people are starting to get real about this. And then lastly, work by Fagans and Rumpf have explored the idea that there may be valuable data sealed within regolith episodes on the moon. Now, they're looking at solar wind emplacements and so forth, so their quarry is different from mine. But the point that is relevant is that the lava flows over various episodes of emplacement of those over time may also have sealed earlier episodes of biological materials that may have made their way to the moon. Model-based maps from Armstrong, I just point these out if you haven't seen them. They have attempted in several different papers to try to quantify where you would get the most likely emplacements and where those would be. And so that's a work in progress by folks like that. What are we looking for? These are the plausibility arguments. Organics, a number of people have tried to look at impact simulations with organics. The good news is that a heck of a lot of that stuff survives. Same sort of thing with microorganisms, specifically bacteria. This is no surprise to those of us who study bacteria. They're tough little buckaroos. And even with direct impacts at the highest velocities, they survive. All we know about lichens is that they remain very viable in space conditions. Whether or not lichens are going to find their way to the moon, who knows? Plant seeds don't do so well because they're bigger and more structurally complex, but the organic goo that remains after you smash them into something is potentially preservable and distinguishable in the lunar context. And then no one as yet has tried to smash animals into anything, but one wonders if the tardigrade form that is very resistant and allows tardigrades to endure many different kinds of insults environmentally might be the candidate to actually try that with at one point. So how will the specimens be affected? I'm running out of time, so let me just say these are all obvious. People have looked at all of the different various parts of the kinds of insults that material on the moon would experience, although most of that has not been looked at vis-a-vis the specific biological context. I think that there is the potential for synergistic destructive or perhaps protective effects of all of these different suites of environmental circumstances that material is going to endure. And so the ultimate question is, how hard is it to be a fossil, quote unquote, on the moon? I'm going to skip over these. I just wanted to show that we were doing our homework and that we're contemplating producing a paper. And after working on this talk for this meeting, I feel even more confident that it's a timely thing to do at this point, to bring all this material together. There's detailed calculations like this one, looking at that heat flow from lava emplacement, how that propagates down through both regolith and basalt. We certainly have many examples of that on Earth, which I did not cite here. Also to look at for analog examples. And so the take-home message is that lunar residing Earth-derived astrobiological materials are distinctly possible on the moon. Probably not an easy quarry to find, but that some very valuable work has been done on scattered aspects of this problem through the literature. It's not a huge amount of literature, but that synthesis of these fragmentary pieces of information and mapping out additional germane information from other aspects of lunar science and, in fact, Earth science can be brought together now. And the goal of this, of course, is not to imagine that we're going to send an entire mission to go hunt around for Earth derived materials anytime in the immediate vicinity, but with the increased cadence of activity and attention to the moon is something that would be helpful if we could sensitize people who are sending missions for other purposes that may bear on these questions to let them know that these materials may be out there and try to educate people about what they might look like, and so that they won't be overlooked. Thank you.
It's delightful, Penny, to see this kind of thinking, because when you look at the decadal surveys of the past and the one coming up now, is there anything at all that indicates that we are going to be looking into lunar lava tubes?
Oh, well, lava tubes are my specialty, and I certainly hope so. You know, I've been writing about them for 25 years, and lava tubes on Mars as well. And I think that, you know, I used to be a single voice being told that there were no caves elsewhere in the solar system, and I think now that we have, you know, clear evidence that there are subsurface terrains on the Moon and Mars and Europa, you know, Io and even Mercury and so forth, that, you know, casting our eyes to the subsurface of these bodies, I think, is very important. And on Earth, we know that, that caves, you know, protect various paleontological, geological, and anthropological materials, and hopefully they can do the same thing on the Moon. We'll see. We'll see. Stay tuned. Okay.